right, so we can go on. Sorry. Last class, when I was talking about the Excel assignment, I thought that I was remembering it incorrectly, and I was referring to kind of problems 2 and 3 as what we did in Excel on Monday. Those are really problems 2A and 2B, right? So we kind of went through examples. We were looking at the sample mean, and we knew the population variance that was given to us, and then we had a sample proportion. So I'm going to push that Excel assignment date up to the end of the day next Monday, because I forgot there was kind of the final question, which is what we're going to be covering today. Okay. But if you had kind of tried to work on it, you would have gotten very, very close. It's going to be very, very similar to what we did on Monday. And I'll kind of show you what the difference is by the time we leave today. Okay. I'm also going to post kind of the next Connect assignment. It'll have some stuff on there that we haven't covered yet, but it'll be really good practice kind of leading up into that next exam, which I think tentatively I had set for next week. But instead, I'm going to push that forward, and I'll put an announcement up on Canvas about this. It should be, we're going to kind of target the date of November 10th. So that following Wednesday. I think originally it was next week. So we'll kind of go to that next Wednesday. Okay. Make sure. So Connect, Excel, exam date. Any other questions from me before we get going here today? Okay. So I think that what I'll do to kind of start us off is what we had before were these two confidence interval equations where we knew that those sample statistics followed followed a normal distribution, and that we kind of turn different values for those sample means or sample proportions into what we call z-scores, right, or a standard normal distribution. And we multiplied that by just the standard deviation of each statistic that we were going to look at. Kind of recall the standard deviation of the sample mean here. We were using this equation. We knew that it should follow whatever the population variance is over the sample size. So what we're going to go, I kind of mentioned this when we were doing this, so we have to kind of walk before we can run. And then this is really goofy. If we're building a confidence interval where the true population mean lies, so we don't know what the population mean is, how do we have the population variance? It doesn't make a whole lot of sense. So in application, what's more likely is that when I see a sample mean, right, I can still build a confidence interval around that. But if I try to use these z-scores and I don't have the population variance, well, what I can do is use a sample variance as like my best estimate for what that is. Okay? So it's going to look otherwise pretty identical to what we were doing before. It's just the notation changes to kind of signal that I was calculating the standard deviation of my sample means not using a known population variance, but only using a sample variance because I didn't know the population variance. The issue is going to be is that I can't actually continue to use that standard normal distribution anymore when I'm building my confidence intervals. Because what happens is I can, without walking through the mathematical proof, I think you have some pretty good intuition behind that. So let's assume that I had my sample and I calculated the sample variance, but then I actually found out instead that was the population data, right? So the equation that we had for everything right over here, we're calculating the sample variance. This goes like way back, right? We said we had to divide by n-1 instead of n. So if I have sample data and then it ends up being the population data, my sample variance would always be a little bit higher than what it should be, right? Because dividing by n-1, a smaller number, is going to inflate that variance. So because it inflates that variance a little bit, when I turn this into a standard normal distribution by dividing by that standard deviation of my sample mean, if this is inflated a little bit, then it's going to kind of alter the distribution of these are no longer z values, but we'll call them t values, because they're going to be coming from a student t distribution. But how much higher that sample variance would be is going to be dependent on what the sample size is. If I divided something by 1 instead of 2, right? N was 2 and minus 1 would be 1. That's going to affect my sample variance way more than if I was dividing by 999 instead of 1,000. So our sample size will kind of tell us how much this standard deviation of my sample means will be kind of inflated. So what we end up with here, where did I put my, even get it out? No, it's right here. So most of the time we don't know it. So we can use that sample variance as kind of an estimate for what that population variance is. We end up seeing the student t distribution instead of a standard normal distribution. Now the student t distributions, right? I actually should make this plural because every single sample size is going to have a slightly different distribution, because every single sample size, right, divided by n minus 1 would have a slightly different effect. Okay? So at every single sample size, we're going to have a different student t distribution if we're only using this sample variance instead of a known population variance. So it's really, really similar. The student t distribution, I mean, visually looks almost identical to the standard normal, right? It ends up being symmetric. It ends up having a mean of 0. So if I'm kind of drawing it out here, it's symmetric. It ends up having a mean of 0. But one of the issues is going to be, because that standard deviation of my sample means is a little bit higher, the variance is a little bit higher, or it's more spread out. Okay? So if it's more spread out, how do I want to do this? Instead of thinking about just the student t, let's say I start out with something that I know, the standard normal distribution. I know that if I want an area of 0.025 in this upper right tail, right, the z value that would give that to me, I can use that standard normal table to find that it would be 1.96. Well, the problem is the student t distribution looks very similar. Each one looks very similar to a standard normal. It's just more spread out. So more spread out, kind of having a higher variance means that it's going to be a little bit flat, right? So this would be like my student t distribution. So when I'm building confidence intervals, if I was using z values over here instead of t values, and I use that 1.96, well, if I use that 1.96 for my student t distribution, notice the area that would be in the tail there is going to be, I drew it really, really tried to emphasize this. It's going to be much larger, right? So I can't keep using those same number of standard deviations away from the mean, the same z values, because it wouldn't result in me having alpha outside of my confidence interval. It's going to be something that's much larger than alpha. So in order to actually get something that has only 0.025, my t value is going to have to be something that's greater than the values I was using for my standard norm. Okay? I kind of walked through, that was kind of that video that I kind of put up on YouTube. Didn't watch it. I would highly suggest it kind of really solidifies this idea of why we have to do this, use a student t distribution. And what ends up being true is that the values we need are larger, right, than from the standard norm. Now, as that sample size gets higher and higher, this n minus 1 doesn't matter as much, right? And so our standard deviation won't be as inflated as it was when we had really small sample sizes. So as the sample size gets higher and higher, we actually end up seeing the student t distributions just start having a lower and lower variance, or a variance that's getting closer and closer to 1, which basically is saying the student t distributions start to get closer and closer to that standard normal distribution as we increase that sample size. Another reason why high sample sizes are good. So usually if we get up to like 100, it's really a pretty good approximation. I'll end up showing you here in a little bit. If we get up to 1,000, it's almost indistinguishable. It is indistinguishable at the second decimal level. Okay? So I think I had a visual here, but I kind of already did this up on the board, where it shows that if we keep using the same values from the standard normal distribution, when we're actually looking at a student T, the area in the tail there ends up being quite a bit larger than that desired alpha over 2 that we want. Okay. So to find, how much higher does this value, T value, need to be than 1.96 to get us that desired alpha over 2 in the tail? Well, to do that, we're going to use a student T table. I don't even know why I have this one in here, maybe just kind of a reminder. And if you're looking back at the slides, but I'll show you the actual table here that I put up on Canvas and that we can start using. Right? So moving forward, we're going to have to probably want to print this out so that you can have it in front of your, make sure you can be able to pull it up on your phone or on a computer when you're in class, because we'll start using it, using iClicker questions and things where you're going to have to look up some of these values. Okay. So the way that we read the student T table is a little bit different than the standard normal. First of all, notice it's looking at the right side of the distribution as opposed to the left. Now, the reason why it's doing this is just so, or why we have it this way, is just so that we can get the positive values here. If we wanted the left side of the distribution, it's symmetric. So it'll be all these same values, just negative. So what we're going to do is use the left side of this table to identify our degrees of freedom. So our degrees of freedom is simply going to be n minus 1, or the sample size minus 1. So we'll look at these degrees of freedom, and what we're calculating what our degrees of freedom is. We'll find it here on the left-hand side, and then define the T value that gives us the alpha over 2 in the tail that we want. These column headings represent the area in the tail. Right? So let's say I wanted that 0.025 in my upper right tail. I go to that column of 0.025. And then let's say I had degrees of freedom of 5. The value that would give me, or the T value that give me 0.025 in that tail would be what? 2.571, which is quite a bit higher than 1.96. Right? So as I continue to increase my sample size, the T value that I need to get that desired area in the tail here of 0.025, notice that T value starts going down or getting lower and lower. Okay, so I keep scrolling. I'll notice once I get to 100, it's starting to get pretty close to that standard normal distribution. Once I get to 1,000, it's the same, it's off by 0.002. Okay? So anytime we have really large sample sizes, we almost don't have to worry about the fact that we're only using the sample variance, because we could just use the standard normal and it'd be a really close approximation. Okay? Any questions kind of about how to kind of use that table or anything that I just kind of walk through? So we'll do two things. First, you'll find your degrees of freedom. Then you'll find the area you want in the tail. Where those two things meet, this table will tell you that's the T value that gives you the desired area in the tail. I'll go you, then you.
So the top says these values are for alpha.
Yeah, so it is a little bit confusing when we look at this. So for confidence intervals, it's a little bit confusing. Once we get to hypothesis testing, it makes sense for like one-sided tests. So if you want to, you print this out, just cross off the alpha there if it's going to confuse you at all. Because all this table, like when it says alpha there, all it's referencing is the area that's in that little picture, right? It's just referencing the area in that right tail. So when we're doing the confidence interval, we still want to find the value that gives us alpha over 2 on each side. It's just when we look it up. So let's say I was, I wanted an alpha of 0.5. So my alpha over 2 is 0.025. The value that I'll look up in that column is that 0.025. Like I said, if it's confusing, you can kind of just cross this off, but it's just using alpha as a placeholder for the area that's in the upper right tail.
So that pretty much
was your question. Yeah.
So to find the area in the upper tail, that's just alpha over 2. To find the
Yep. Yeah. So you can think about it as that you want. You've got like you're trying to build a confidence interval. You've got alpha over 2 in each tail. So to get the T value that gives you alpha over 2 on each side, you just look up the one side. Okay. Any other questions? Okay. So another kind of handy thing about this table, makes life, I think, a little bit easier, but sometimes it can be confusing to people. So if you look at this very last row, it's got an infinity sign, right? So what happens is as our sample size is getting larger, our student t-distribution is getting closer and closer to a standard normal. If we could theoretically have an infinite sample size, right, then it would be exactly equal to what that standard normal distribution is. So this last row, you want to think about it as, this is kind of like your comparison group. These are the values that you would find for those desired areas in the tail if you use the standard normal distribution. So notice 0.025 from that standard normal distribution, the z value that would give you that desired alpha would be 1.96. So that last row of the student t table is almost like they just added in the values you would find if you were to look up those areas on the standard normal, right? And I also think, hunting through to find, okay, what's the value closest to 0.9? Okay, I'm in between two, I can only go to the second decimal. That's a little bit more difficult, especially when we're looking at confidence intervals. So whenever if I was doing this myself, and I had a known maybe I had a proportion and I know I need to use the standard normal distribution, I would just pull out the t table and go to this very last row. And that way I can actually get the z value I need, not to the second decimal, but actually out to the third decimal here. Notice like a lot of these, we were usually in between 1.64 and 1.65. Well, I can actually get the value out to the third decimal, which is 1.645 from this table. Okay. Any questions about that? Okay. So we've got the student t table. And if we put everything that we've just kind of said together, we've got our confidence interval equation, which is kind of up there on the board. All right. Once we plug the values in, though, it's going to look procedurally no different than what we were doing when we had a known population standard deviation. Right? It's just that we're going to have to look up that number of standard deviations away that we need to go. That's going to come from our student t distribution as opposed to our standard norm. Okay? So the steps are really the same. It's just we use the sample variance to approximate what the population variance is. We have to use the student t distribution, which requires us to find our degrees of freedom, or n-1. But really at that point, it's just kind of a matter of plugging all of our values in. So we'll work through a couple problems here. So the first one doesn't really have a lot of context to it, but it gives us some values to use, and it kind of allows us to see how this is going to come together. So let's say I had a sample of 36 observations, and I don't have a known population variance. All I have is the sample variance that I can calculate from that sample. So I've got my sample mean is 9, my sample variance is 324, my sample size is 36. That's 3 of the components that I need. The only thing left to do is look up that t value. I mean, on the exam, you'll have the formula sheet that has this confidence interval equation. So hopefully, like if I'm giving you this, even using the only thing I didn't use notation on was the sample size, 36, right? But if I had said, n is equal to 36, s squared, or the sample variance is 324, x bar, or the sample mean is 9, all I'm doing is taking those values and just plugging them in where they fit into the equation. The kind of hard part would be, we'll now have to look up that t value.
Just a quick question. Are we going to have the tables and t tables?
Yeah, so on the exam, I'll give you formula sheet, standard normal, and a student t table. And I should be getting some practice exams up tomorrow at some point. So I'll create like a folder on Canvas that says exam 2 study materials or practice materials. And I'll put a couple practice exams in there. And I'll also put the formula sheet that you'll have in there as well. Okay. Any other questions? This is a good one. So I just start plugging things in, right? My sample mean was 9. I add to get my upper bound, I subtract to get my lower bound. I don't know the t value yet, right? I've got 324 as my sample variance and 36 as my sample size. So I'm going to look up that student t value. Right? Well, the first thing I need to know is what alpha am I looking up, right? So I've got an alpha of 0.01. What level of confidence would my interval be for? confidence. Yeah, right. So alpha is just the percent outside of my interval in decimal form. So 0.01 corresponds to a confidence level of 99%. So my alpha is 0.01, which means alpha over 2 would be 0.005. And what would my degrees of freedom be here? Yeah, it's simply n minus 1, so 36 minus 1, which is 35. Okay. So I go to that student T table. I'm going to scroll up here. So my degrees of freedom is 35. The desired area in each tail, right, or the area that's in the upper right tail and the area that's in the lower left tail would be 0.005. So I go over to where those two things meet, 2.724. So now I've got that T value. Now it's just a matter of getting this entered into a calculator. Like I said, similar to the other examples, maybe calculating this standard deviation of your sample means ahead of time and then just having one value to plug in might make the kind of computation a little bit easier. Remember, I'm adding to my upper bound, I'm subtracting to get my lower bound. But other than that, it's pretty similar to what we were doing before once we find that T value. Okay. So if we go back here, oops. All right, so I could kind of find that intermediate value, which was 3. Now it's a matter of plugging everything in. I get my lower and upper bound. Now there's not much context to this example, so I'm not going to do any interpretation of this confidence interval. And I did break this down. Someone in my earlier sections asked me, where's that 8.16 come from? Well, remember, we can kind of refer to what we're adding and subtracting to our sample statistic as our margin of error. It's not quite as useful when we're looking at sample mean examples. We talked about how that margin of error is like used in political terminology, even when we're looking at the sample proportion. But if we wanted to, we could go ahead and first calculate the margin of error, and then we just have one value that we have to add to our sample mean, one value to subtract from the sample mean to get that lower and upper bound. So you can kind of just breaking it up into more parts just to make it a little bit easier, like getting entered into a calculator. Are there any questions over anything here? Yeah.
So all this information we were given, are we always going to be given all
So,
this data?
yeah, like on the exam, I will tell you what the sample mean is. I'll tell you what the sample variance is. Really, what skill you need to have to do confidence intervals on the exam is to be able to use those tables effectively, and then also your calculator basically. But really kind of looking up those T values and Z values is what's going to be important. In practice, you would have a data set, you'd calculate the sample mean, you'd calculate the sample variance, just like we did kind of in the first exam kind of stuff. But for the sake of like time on the exam, right, I would give those to you. Any other questions? All right, so let's do one that has a little bit more context to it. Okay. So let's say that the AMA, or the American Medical Association, states that the average salary for physicians is $175,000. You don't believe that, so you take a sample and you find a sample mean of 160,000. Now, this is like maybe, I don't know, speaks to who I am as a person, but one of the nice things about confidence intervals is basically if someone comes to you and says something, if you had a sample, you can always determine whether or not if that's potentially true. You can always rule it out, right? At least with a certain level of confidence. So here, I've got my sample mean of 160,000. I'll then add and subtract my margin of error to get my upper and lower bound. I can plug in the rest of the information I know, which is for that standard deviation of my sample means. Excuse me, we said that that was the square root of the sample variance. So that's 324 million here, just kind of big. And then my sample size, I had 81 physicians with the sample. So the only thing left that I need to find was that T value for alpha over 2. So here, what level of confidence do I have that alpha is 0.05. Yeah,
99%.
so alpha is 0.05, right? So that's the percent outside the interval in decimal form. So, yeah, so 95, right? So I've got my 95% confidence level. Alpha is 0.05. And obviously, you don't need to have that to necessarily solve this problem, but I'm just trying to kind of get us to think about it so that we're clear that if I only give you the confidence level, you can determine what alpha means. Okay? So alpha over 2 would be 0.025, and my degrees of freedom here would be what?
80.
Yeah, just n minus 1, so 81 minus 1 would be 80. So I go to that table, I've got my degrees of freedom of 80. The area I want in the upper right tail would be 0.025, right? Half of alpha in each side of the interval. So 0.025 is the area I want. I scroll down here to my degrees of freedom of 80. 1.66. Oh no, I think I jumped columns. Did I? Yeah. So here's the column I want. Degrees of freedom of 80, 1.99. So now that I've got that t-value, I plug that in as 1.99. And now it's just a matter of getting this entered into my calculator, file my upper and lower bound. One thing I also mentioned when it comes to like the exam, I'm never going to give you a degrees of freedom. Notice how it starts to make some like big jumps here. I'll never give you a degrees of freedom that's like, oh, well, it's in between 80 and 100. I don't want to do something like that. It'll be one of those exact values on the left-hand side. Questions on that one? So if we go ahead and do the actual computation here, and you can calculate the intermediate step, or you could do, break this down into steps if you wanted to. You don't have to. I'm kind of writing this all at once here. But if I want ahead of time calculated that standard deviation of my sample means, I could have just plugged in 2000 there. Notice one thing I also will mention to not get confused on is you're only doing n-1 to identify what student t-distribution you need to use. Notice when it comes to the actual calculation of that standard deviation of your sample means, you're still using the sample size, right? So I'm still using 81. But if I go ahead and figure out what this upper and lower bound are, I get 156 to about 164,000, right? So I can do the erasers over here. So I've got 150, what is that, 154, 156 to 164,000. So with 95% certainty, I can say that the true population mean for physician salaries here is somewhere in this range. So when I go back and look at that reported amount that the AMA was giving, which was 175,000, well, I could turn around to the AMA and say, look, you're giving, aspiring physicians false hope. I mean, it's not that far off, but right, 175 is definitely not in that confidence interval, right? So if I wanted to be able to say something with 95% confidence here, the only values that I couldn't tell someone that they're wrong on would be values that are within this range. Questions on? All right, so I think I've got this slide here that kind of summarizes some of the new functions that we'll be kind of looking at in Excel. It's really not wildly different than what we have already been doing. So we'll kind of jump into that, do a little bit of Excel work, and then I'll probably introduce the next and final topic for this upcoming exam, which is hypothesis testing. Okay. So we're going to use that same file that we have been. So after today's class, I'll post kind of the completed version. I mean, we've done all the work in class and any of the blank stuff there we filled in. So I'll kind of save this after we're done with class today, and then I'll repost it once I get back to my office. So I'm going to rebuild some of this because I didn't delete this. I forgot to, I only made the one slide blank. Although Is there anything interesting I could do here? We'll use this third worksheet. All right, so unknown population SD. Okay. So I've kind of actually on this data set. So I'm going to just delete these t-values in my upper and lower bound. I'm going to delete these guys right here. Go over. I've kind of got like two data sets here in one. Notice there's like a column that separates them. So here's a bunch of counties in 2012. Here's a bunch of counties in 2016. Okay. Now I've got drug deaths per 10,000 people here in each of those years. So what I'm going to do is simply take the average of that like death rate, right? Drug death rate. Hopefully we're pretty comfortable doing this in Excel at this point, right? To find our sample mean. And maybe to kind of be real clear here when I post this, and right, this represents my sample mean. And down here, I'm going to calculate my sample variance. Well, we've done this before, right? And I'm just going to copy these, paste them down here so we kind of recognize these are all samples, right? We've done that sample variance before. That's just var.s, right? And we're just selecting the entire variable. So I'm not going to go through that again. We've gotten quite a bit of practice, I think, at that. So down here, what I need to do is find the t-value that gives me the desired alpha over 2 in the tail at whatever my degrees of freedom are. We just saw that how we can do that using the physical version of that table. But that table was somewhat incomplete, right? In fact, I'll actually add a different alpha in here just to show you, like, we couldn't really do this one in the table. So let's say I wanted to do something like an alpha of 0.03. Well, if I go to that table, right, I don't have, that's not one of my 6 values here, right? If I really wanted to look at every single possible area in that tail, this table would be so wide, it wouldn't be very practical, right? But Excel, right, it doesn't necessarily have to kind of be restricted to a table, because remember, these values in the table are really coming from integrating the density function. We said that's not fun to do. And so people have already done it for us and created these tables, but in Excel, it'll actually do the integration behind the scenes for us. Okay? So when we were looking at an example on Monday where we knew the population standard deviation, we used that norm.s.inv function to find that z value that gave us alpha over 2 in each tail. So very similarly, we're doing the exact same process. It's just that we're, instead of using the standard normal, using a student t-distribution. So instead of norm.s.inv, all we do is use the t.inv function. So if you had set these confidence intervals up before, based off of what we did on Monday, everything would be correct except for you shouldn't have been using norm.s.inv, you should have been using t.inv. Because we only had a sample variance there for that final kind of problem 3. Okay. So the first thing I have to tell it is the area that I want in each tail, right, which is, or on each side of my confidence interval, which is alpha over 2. So I had up here earlier, but just as kind of a visual reminder, right? What we're really doing there is looking for these t-values that give me alpha over 2 in each tail. Okay. Now, the problem is going to be if I treat this like the normal distribution. Oh, I forgot. This function actually needs 2 things, right? So I have to put a comma. The second thing I need to tell it is, well, which student t-distribution am I using, right? What's the degrees of freedom? Well, that's simply just going to be my sample size, which I have up here, -1. Okay. So now that I have this, it should give me that t-value that gives me alpha over 2 in the tail. The only problem is, just like that norm.s.inv, it's always looking at that left side of the distribution. Right? So unlike the physical table, the function works, right? It's just integrating, kind of giving you the cumulative, right? It's looking at that left tail, everything below a certain value. Well, this is the value that we want, right? But that's the one we need for the lower bound. We need the same value at positive for the upper bound. When we actually type in these equations, those signs are already built in. So we said we just need the absolute value here. So we could use that absolute value function, close my parentheses. Now, if I try to copy this down so that I can get the t-value that I need for these 4 different levels of confidence pretty quickly, what's going to be a problem? Yeah, the sample size cell reference is going to start moving down as well. I want my alpha value to change, but I don't want that sample size to ever change. So I'm going to put, oops, it's my F4 button. Not, oh, that would help, wouldn't it? I accidentally deleted that. There we go. Oh, I want you to be able to see this. So all I did there was F4 or Command T on a Mac to freeze that cell reference. Now when I copy this down, I'm getting all these T values pretty quickly, okay? Any questions on that? You want to see one of those cells again? Or... So now it's really just kind of like what we did on Monday. Now I'll show you here how you do it all in one cell. I think on Monday, I broke it down so that I calculated that standard deviation of a sample or sample mean or a sample portion in a different cell. Here, I'm just going to do it all on one line. So kind of like I have the equation written over there on the board or right here, right? We're not going to kind of calculate the intermediate or use the intermediate step, but it's, you know, you could do that here as well and it'd be fine. So I'm going to take my sample mean. I'm going to subtract that T value or the number of standard deviations the way I want to go below that sample mean to build my confidence interval, and then multiply it by whatever the standard deviation of my sample means is, which is just the square root of my sample variance divided by my sample size. Okay. Similar to the examples that we did on Monday, the only thing that I want to change when I'm calculating the lower bound for different levels of confidence, only thing I want to change is that number of standard deviations away I'm going or that T value. So everything else, I'm going to freeze those cell references. Okay. Hit enter. Well, actually, instead of hitting enter here, I know that when I want to calculate the upper bound, it's going to be this exact same equation. So I'm going to copy that, hit enter to get out of the cell. So I'll paste this over here. And the upper bound is going to be the exact same thing. It's just that I add my margin of error. Okay. I hit enter. Now when I copy these down, I've got 4 different confidence intervals pretty quickly. Okay. And notice I can even do weird values like alpha of 0.03, which I couldn't have used that physical table to do. Okay. Any questions over anything there? I went through a little quicker than, but yeah, like I said, once we get to that point, it's very similar to what we did on Monday. Oh, I thought there was something I wanted to point out here. Oh, so there are, let's see if I can even remember what they are. So there's these confidence.norm and confidence.t functions. I would, you know, I don't teach them to you for a reason. I think they're a little bit more tricky than if you just kind of construct this on your own. Also, we're going to start doing some confidence intervals after this exam with 2 populations, and these don't quite treat them correctly all the time. So I don't show you how to use these, and they're actually going to just find what your margin of error is. They're not actually going to give you your lower and upper bound. So I would even say the name of them is actually, they should change the name of these functions. But if you Google how to do this, you might find this confidence.norm or confidence.t. I don't want you to do it that way. I mean, if you do it and you use it correctly, I'll give you full credit. I've just like, of the people that don't listen to me in class and then Google it and find this and use it, I would say maybe 5% of them do it correctly. So I would not suggest that strategy. I've got this, you know, template up there for you. It's a really good, template for how you should approach that Excel homework. And also, like I said, those functions later on for future topics will start to not work for us. So I want to, you know, make sure we know kind of how to set it up this way. Okay. All right. So I can do the exact same thing for 2016. You know, at this point, like, I don't really need to type this in again. It should be the exact same student T values here, because I have the exact same sample size. Actually, yeah, because I have the exact same sample size. So I'll type in my lower bound equation. I'll take the sample mean, subtract that t-value, multiply that by the square root of my sample variance over my sample size, right? It's the exact same thing I did for 2012. I'll then freeze the cell references for everything except for that t-value. I'm then going to copy, hit enter, paste, and change that to add the margin of error as opposed to subtract it. So I've got one confidence interval. Now I've got two confidence intervals. Okay. So the reason why I kind of had these 2 years, I originally thought we might find something interesting about drug deaths. I always hear like, people don't like Indiana all the time. People say, act like there's this huge, I mean, there is a problem, but they're acting like, drug use and everything is skyrocketing. I was looking at it and I think the mean in 2012 up here was what, 2.45. So if we just look at the sample means, it does look like drug deaths have kind of increased over this 4-year time period. But if we look at the confidence intervals, remember, all we have is sample data. Now I have this broken down by county, so probably wouldn't want to think about this as a sample of Indiana, more so like a sample of kind of the entire country. But if we're basing off of Indiana, have drug deaths actually increased? Well, I mean, if we look at 2012, well, even at the 99% level, or we do 90%, 2.16, 2.73. And then if we plot 2016, what, 2.19 to 2.8, so you notice these confidence intervals almost overlap each other entirely, right? They're a little bit shifted, but there's a significant amount of overlap. So I can't really say anything about whether or not drug deaths have increased or decreased, right? Because the true population means could be anywhere here, right? So the relationship between them could be greater than, less than, even equal to each other technically. Any questions? Now, if we did come up with some confidence intervals that didn't overlap, and maybe this was 2012 and this was 2016, then I could actually say with 90, whatever percent confidence, depending on what confidence interval level I was looking at, that drug deaths have increased, right? Because I know even worst case scenario, if these didn't overlap, if the true population mean in 2012 was here, true population mean in 2016 was here, right? It would still be greater in 2016. Any questions over Excel or related to the student T distribution? So we'll get a little bit of a head start. I don't know how far the other section is going to get this week, but for you guys, I'll give us a little bit more time next week to cover this stuff. So we've got the final kind of topic we'll be looking at is hypothesis testing. So it's kind of similar. I mean, it's related to, I should say, confidence intervals, but it's a little bit different. So what we're going to be trying to do with hypothesis testing is pinpoint rule out certain values for the population parameter we're interested in. So we can do hypothesis testing for the population mean. We can do hypothesis testing for the population proportion, right? But I'll kind of start out just showing you how we would do it for the population mean. Okay? So we want to test kind of where this true population parameter is. So we develop what we call a null and alternative hypothesis. Right? So the way that we're going to kind of write the null and alternative hypothesis is H subscript 0. And the Connect homework or the book will sometimes call it H subscript 1. I always write it as H subscript A. I just think it makes it easier. But it's basically our alternative hypothesis. So we're going to have some hypothesis. We're then going to look at our sample and say, does our sample support that hypothesis? If it does, okay, great. I'm not going to reject it. But if it goes against my null hypothesis, I potentially can then reject that what I assumed that was true about that population parameter is actually true. So I might do something like this. What if I was, maybe I'm thinking about the average income in the US. So maybe I assume that it's 50,000, or that true population mean is equal to 50,000. The alternative hypothesis would then be kind of like the complement of that, right? So if I'm assuming it's equal to 50,000, the complement of that is that it's not equal to 50,000. I then take a sample, right? So maybe I take a sample and I see, I don't know, 45,000. Now, that is, that's a sample evidence that goes against what I assume, right? I assume that the mean was 50,000, my sample mean is only 45, so that's evidence that goes against my assumption. However, depending on my variance, right? If what I assumed to be true was in fact true, then what we know about the distribution of sample means is that they should be centered around that value. And potentially seeing 45,000 isn't that unlikely if the true mean was 50,000, especially if I have a relatively low sample size, right? So even if we find evidence that goes against what we assume to be true, we may not reject that assumption. And whether or not we reject it is what we're eventually going to be able to do with this hypothesis testing. I'll have to show you how we determine whether or not is this evidence that goes against my assumption enough, right? Or does it not go against it enough, right? Now you can imagine different values, like 45,000, yeah, maybe, if the true mean was 50,000, I could see that as a sample mean. However, if I saw a sample mean of like 15,000, well, it seems like my assumption is definitely probably wrong, right? So if I find evidence that's really inconsistent with the null, right, it's a little bit easier to envision, oh yeah, definitely I'm going to reject what I assume to be true because I found something that's wildly different. So that's kind of where we're going. If we have sufficient enough evidence, we can reject the null, but if we don't, right, it's something that goes against the null, but not very much, then we're not going to reject it. Right? Or we say we failed to reject that, or we didn't find strong enough evidence to be able to reject our assumption. So kind of the example that I'll kind of introduce, and we'll probably finish this more on Monday, is let's say that I want to test for whether or not the average mass market beer has a lower ABV than, I don't know, Bell's Too Hard, which is 7%. Right? So that's what I'm wanting to test for. So that's what we're going to call kind of my alternative hypothesis. So I take a sample and I find that from 36 different mass market beers, the average ABV is it 4.5? Yeah, 4.5. Okay. So if, for a second, I assume that mean is 7, I know my sample mean should be normally distributed around that value, but I saw a sample mean of 4.5. Okay. So how do we identify what the null and alternative hypothesis are here? I kind of plug this value in. But if we wanted to actually write out my null and alternative, how would I do that? Well, the null is going to be our assumed true state. I kind of already cheated. I kind of worked ahead here. And the alternative hypothesis is going to be what we're trying to find, right? So anytime I have a question, right, and I think, okay, I want to test to see whether or not the average income in the US is not 50,000. Maybe someone told me that it was. So I wanted to take a sample and try to test for whether or not it is equal to 50,000. Or sorry, if it's not equal to 50,000. So I assume the opposite is true as my null hypothesis and stack the deck against myself. Hopefully, as we work through kind of more of this topic, we'll see why kind of making that assumption stacks the deck against ourselves, like assuming the opposite of what we want to find. But for now, whatever you want to test for, that's your alternative hypothesis. So you stack the deck against yourself with the null and assume the opposite is true. So if I'm thinking about how I write this out, right? No, I want to stick this on the back. Did I put these out of order, probably? Or maybe I'm just thinking out of order. Here we go. This is the slot I want. So we're going to have really 3 different types of hypothesis tests, right? One, where I want to test to see whether or not that population mean is greater than a certain value. So mu subscript 0, kind of representing the assumed true mean, right? So for a greater than test, or what we'll usually call a right tail test, I'll have a greater than sign in my alternative hypothesis. I want to test to see whether or not the true mean is greater than a specific value. So I assume the opposite is true, which is that it's less than or equal to that value. I then have a left-tailed test, which is when I want to test to see whether or not the population mean is below a certain value. Right? I stack that against myself in the null and assume that the opposite is true, which says it's greater than or equal to that value. I then have what we call a two-tailed test, which is maybe I just want to test for whether or not that true mean is different than a certain value. So I stack the deck against myself and assume it's exactly equal to that value. Now, notice for these first two, only evidence on one side would go against the null hypothesis. For a right-tailed test, only finding a sample mean that's above whatever value I assumed it was actually would go against the null. For this left-tailed test, only seeing a sample mean that's below this assumed true value would go against the null. So we'll call these one-sided tests. However, for the not equal to test, right, if I've assumed that the mean is 50,000, well, if I see a sample mean of 45,000, that goes against it. But also if I see a sample mean of 70,000, that will go against it, right? It doesn't matter which side of that assumed true value I'm on, I could still see evidence that would go against that null. So we'll call that our two-sided test. So we've got three different types of tests. Go back here. Just skip these slides. And we really have kind of three outcomes, right? Once I've identified what my null alternative hypotheses are, either I find evidence that supports the null, right? So if I find, here we go. If the evidence is not inconsistent with the null, or like I found something that aligns with it, say I find the sample mean of exactly 50,000, well, then I'm not going to reject what I assumed. I'm not going to reject that null hypothesis. Potentially, I find some evidence that goes against the null, right? So it's inconsistent with the null, and it's inconsistent enough that I can reject it. That was like my example over there where I said, what if I saw a sample mean of 15,000? And then the third scenario is that I find something that's inconsistent with the null, but not very inconsistent, not inconsistent enough to reject it. So those are kind of our three different outcomes that we're going to see. So I'm going to try to use a court case analogy to hopefully have like a slightly better understanding of what we're doing here with this null alternative. So let's say, why is somebody in a court case, or why would you be in court? They are trying to find whether or not you are guilty. Right? That's what they want to try to find. Otherwise, they would just let you go on about your merry way. Right? They brought you in because they think you're guilty. So that's what they want to find. That is what they're trying to test for. That's going to be their alternative hypothesis. Right? So that's their alternative hypothesis. What would the null hypothesis be? What should it be? Yeah, you assume the opposite is true, which is that you're innocent until proven guilty. Right? So the null and alternative hypothesis here should be that the defendant is guilty is the alternative, and that the defendant is innocent is the null. So what do? They go out. They think that you murdered someone. They try to find, was there DNA evidence at the scene of the crime? Do you have an alibi? Like, did you own something similar to what they think the murder weapon was? Whatever. Maybe I'm watching too much like true crime. But they try to find all this evidence. If they can find enough evidence, right, and they reject the null, which is that you are innocent, right, then you go to jail. So if we have sufficient enough evidence to reject the null, right, we reject the null. And if the null is that you're innocent, we find enough evidence that goes against that, we reject the fact that you're innocent. Right? But maybe, there's no real DNA evidence, there's nothing linking you to the person, the only thing was that you just didn't have an alibi. So if you don't have sufficient enough evidence, then we don't reject the null and you go free, right? That assumption of you being innocent doesn't change at all. Okay? So that's kind of the analogy of using a court case to thinking about what we're doing here with our null alternative hypothesis. And then I had, I guess I can move this guy. I had some OJ pun there. But right, you can kind of think about this is actually a pretty good fit, and it's really exactly what we're doing. It's just our evidence is our sample mean. So went through this, talked about 1, 2 tailed tests. So So the steps when we're trying to identify what the null alternative are, first we have to know, are we looking at a population mean or a population proportion? This one is kind of dumb. I mean, hopefully we can identify this from the problem. Usually this one's easy step. We do need to determine what type of tailed test we have, one or two. Okay. And then we're always going to have to make sure we have some sign of equality. Now, just the practice, like what I always say to just think about it as, just always include that equality in your null hypothesis. Once I walk through some stuff with you, we'll eventually find out that it doesn't really matter if that equality is on the null or the alternative. But just out of convention, I typically kind of always put it in that null. Right? And most people do. But it ultimately will end up seeing it doesn't quite matter. But we do have to have it in one of them, right? So we return to our example of our null alternative hypothesis. If I want to test for whether or not the average ABV is below 7%, that's what I want to test for. So my alternative hypothesis is always what I'm trying to find or what I'm trying to test for. So here, it's very easy to identify. I want to test for whether or not that mean is less than 7% or less than 7%. So for the null, I stack that against myself, and I assume the opposite is true, which is that what? The mean is greater than or equal to 7%, right? It's kind of like going back to the idea of confidence. Now, if I look at this null alternative, I can always identify what type of tailed test I have based off my alternative hypothesis. There's a greater than sign, it's a greater than or a right tailed test. If there's a less than sign, it's a less than or a left tailed test. It's a not equal to sign, we say that's a two tailed test. So, kind of walk through this on the board, all right? We could write out what we're doing in words. That doesn't really help us in the statistics class too much. We actually need to kind of write this out in terms of what our statistic we're interested in is. Right? That population mean being less than 7%. Okay. So we'll use this one. I don't have the icon just pulled up here, so let me. Could have sworn I did. Maybe not. Where are we at in time? Oh, okay. So hopefully we're thinking about this correctly here. We just identified the null alternative hypothesis for kind of our base example. Right? So let's instead assume that we've got a sociologist or an economist who wants to test to see is the mean retirement age different than 67, right? So really what we're saying there is what I want to test for is this population mean any other value than 67? So if that's the case here, what would my null and alternative hypothesis be? So I'll give you about kind of 45 seconds to kind of go. Yeah.
So what determines which test you use? I know in this one it has specific words, but in the last example we did, what made it the less than?
Why is it less than? Yeah. So here, right, what I want to test for is whether or not this average mass market beer has lower than. No. So what I'll typically do on like the exam, I will use these phrases of less than, greater than, and different than. Okay. So if here we've got it, we want to know is it different than 67? Which of these would be kind of my null alternative? So I'll give you 45 seconds here. We'll kind of a little bit of time to think about this. No computation, so. And I repeated two of the answers just because I couldn't come up with a fake answer. So. All right, if you haven't gotten an answer in, take your best guess here. There's 22 of us here today. So if I want to test for whether or not it's different than 67, or I said any other value than 67, what should my alternative hypothesis be? That population mean is not equal to 67, right? Any other value different than 67 would mean it's not equal to 67, which I then assume the opposite is true, which is that it is equal to 67. Okay? So hopefully these different than ones, these two-tailed tests, are a little bit easier to identify. Okay. Any questions on this before we kind of keep moving here? Okay with this? Yeah.
So the first one was lower, like, I think it said lower than.
Yep.
The first example. And then, I guess basically the question is like, how do you know which one goes to alternative again?
Yeah, so the way that I'll always phrase things, there's two ways. So whatever you're trying to test for, that's your alternative hypothesis. You can also say whatever I'm trying to test against would be my null. I usually don't phrase things that way because in practice, like you want to find something. Like here, I wanted to see, does the average mass market beer, is it less than 7%? Well, that's what I want to find. That's what I'm trying to test for. That's what goes into the alternative hypothesis. So usually from like the word, whatever the word problem is, the way you identify that alternative, you'll be identifying the alternative first, right? I want to find this. Is it less than 7%? Is the mean retirement age different than or not equal to 67? And then from that alternative, I can determine the null because it's just the complement or like the opposite of that. Does that make sense? Yeah, it is a good question. Like, especially if you read the book, I don't know. In practice, nobody says like, I'm going to try to test against this. So usually like things aren't phrased in terms of the null. Usually any scenario in the real world, you would like, well, this is what I want to find. This is what I want to test for. This is what I want to use my data to test for. Like, see if it's not equal to 67, see if it's less than 7%. So I'm going to stack it up against myself and assume the opposite is true. All right, so when I'm assuming that opposite is true, it's kind of weird that you would ever be given the opposite of something first without knowing what the original thing is. But yeah. Okay. So what type of tail test do I have here? We call this kind of a two-tailed test, right? Because evidence on either side matters. So maybe type 1, type 2 errors. I'll end this on this. So we'll come back to this on Monday. Or actually, I should have left that up here. Okay. So we've got this 7%. Okay. Remember when I was writing this in general form? I said I'm assuming that the mean is a certain value. That assumed value is whatever value I have there in my normal term hypothesis. So if we, for a second, just take that assumed true value and treat it as though it is in fact true. Right? We've assumed it's true. We'll treat it as though that's the population mean until we have, determined that it's not, right? And until we determine whether or not I can reject it. If that was in fact the true population mean, my sample mean should be centered around that, right? So when I see a value for my sample mean of something like 4.5, well, for a left-tailed test, right, less than or left-tailed test, the only evidence that would allow me to reject the null is if I see something that's on the left side, right? You kind of think about it this way. Evidence that allows you to reject the null would have to support the alternative hypothesis, right? And the only way that I can see something that goes against the null is if that sample mean is less than 7, which would then kind of support that alternative hypothesis. So I see this sample mean of 4.5, and I know that my sample mean should be normally distributed, right? So if I have a normal distribution, and here we'll assume, I think the value I end up using is 1 for the this population variance? Well, as long as I have a known population variance, I know that I can take any value for that sample mean, and I should be able to turn it into a what? A z-score. Now, we're going to start calling these z-scores something slightly different, which are z-statistics, right? But it's really the same thing. So the way that I'll calculate this, so we'll call this like the z-stat, my sample mean. We'll just take that sample mean value, subtract the assumed true mean, right? And then divide by that standard deviation of my sample means, which I know is simply the square root of population variance over sample size. This is something we've already done. It's just we're giving it a different name because instead of using the true population mean, we're using an assumed true population mean. That's the only reason why it has a different name. In practice, it's really treated the same thing. Our test statistic will tell us how many standard deviations away from that assumed true value our sample mean was. So I can convert this into a z-score. I can then find what's the probability that I saw a z value or a z statistic here as low as I did or anything even lower. Right? So what's the probability that I saw something this far away from that assumed true mean or anything even further? If this starts to get relatively low, like let's say this was 0.01. Well, if the probability of me seeing this sample mean is 0.01, if in fact what I assume to be true is true, well, that seems really unlikely. It's probably more likely that instead of that true mean being 7, it's probably way more likely, now I'm gonna have to erase this, but probably way more likely that the true distribution looks something like this, and the true population mean is actually much lower, right? Because then seeing a value of 4.5, well, it makes a lot more sense. That was a fairly likely value for me to see. So the idea of what we're doing is we'll have this assumption. We might see some sample evidence that goes against it. We're then going to determine how likely was it then for me to see sample evidence that went against this assumed true value. And not only how likely was it for me to see it, but how likely was it for me to see something that went against it that much. What we're then going to end up doing, well, so I would like take that 0.01. We're going to end up setting some threshold value where we're like, look, if that probability ever falls below 0.05, I'm okay rejecting my assumption, right? Because what I assumed, it would have been very unlikely for me to see the sample mean that I did. So it's way more likely that that population mean is much lower. So we'll set these thresholds. We'll kind of talk about what they are on Monday. Also, for those of you kind of around here, I don't really care much because I got a pretty thick skin. Well, such like a lot of professors probably will kind of take you leaving early before they stop. So maybe a little bit, I don't know. They might not be too happy with you. So if I'm giving you advice, if you're not in my class, I'd probably kind of wait until they kind of give you some kind of cue that you can leave. But that's all I've got for today. Thanks for you for hanging around. If you are working on that Excel assignment and have questions, I actually am not be in my office today. So if anyone stopped by, I apologize. I'll be around for an extra hour tomorrow, or I'll have open office hours for an extra hour. So instead of just 11 to 1, I should be there from 10 to 1 in my office if you want to stop by and get some help with that. Okay. All right. Have a good weekend. It's not the weekend yet, but I won't see you guys until Monday.